Okay, right, we're going to look at the 1H NMR spectrum of ethanol. We're going to use this as an example to explain how what you can work out from the NMR spectrum of a compound. Okay, so we'll start off. We'll think, all right, what is the structure of ethanol like? Okay, as ethanol. Now, if you look at the spectrum on this axis, which will be marked in ppm, and don't forget what is really happening here as we go in that direction, increasing the magnetic field strength. On this axis, which is not usually marked on an NMR spectrum, it's not labeled, that is the absorption of radio waves. We're going to have okay, we're going to have 3 peaks. So this is a bit low resolution. So if you look at the spectrum of ethanol, you see something like this. You'll see 3 peaks. Okay, you see 3 peaks because if you look at the structure, you've got 3 different proton environments here. But these 3 protons, which are all in the same environment, you've got those 2 there, and you've got the the one from the alcohol. That's a separate environment. Okay, now you can probably guess which peak corresponds to which hydrogen environment. This is 3 hydrogens, and so this is going to be this bigger peak here. Okay. This one is 2 hydrogens, so that's going to be 2/3 of the area of the red peak, and then finally this one is going to be 1/3 of the area. So this area under the peak, this is called the integrated value or the integrated trace. Okay. And what that tells us is it tells us the number of H's in a particular environment. So the apart from the area under each peak, the other obvious thing, I should put ppm down there onto that scale. The other obvious thing is about each peak is where it is on the ppm scale, where it is on the x-axis. Okay. Now this is called the chemical shift. Sometimes given the symbol delta as well. Okay, the chemical shift. Now the chemical shift depends on the environment of the hydrogens giving that peak. How close are they to electronegative elements? How close? And in the exam, you're given a list of ppm data for different hydrogen environments, so you don't have to remember them, but there aren't that many really, and you probably will remember the more important ones. So if we have a look at the let's have a look at the red peak first of all, the CH3. This is got a low ppm, that because those protons are far away from any electronegative element and well away from the oxygen. Let's look at the green peak. That's got a ppm of about 4, and that's fairly typical of when you have H's which are attached to a carbon which is also attached to an oxygen. So that's why that peak is there. And then finally, do we just talk about the yellow peak, the alcohol peak. That's alcohol hydrogen. That's fairly typical of an alcohol hydrogen. Okay, so there's the there we have the two of the two of the characteristics of each peak. So it's basically its area, its integrated value, and then its ppm, where it is on this scale. Okay. Now there is a lot more information that you can gain from a spectrum. If it's not, look, this is at low resolution. If you look at high resolution, you'll see that each of these peaks is split into several smaller peaks, and that gives an awful lot of information. So let's have a look at this at high resolution. Okay, so I just do that. Right, let's see what that peak, what that spectrum is going to look like at high resolution then. Okay, so same scale there. Okay, so we will see that this peak here at ppm of about 1 is actually split into 3 small peaks. The one at this one at 4, the CH2s, that is split into 4 peaks. And the OH one, that isn't split at all, that's just 1 peak. Okay, so I'm going to draw the structure of ethanol again here. Okay, and use the same colors, red, green. Okay, so we need to have a little think about what can splitting tell us about the compound. Okay, this is called splitting then, when you get the big peaks which are split into smaller peaks. Right, we're going to use something called the N+1 rule. Okay, so let's look at the red hydrogens. Okay, you look at the N+1 rule, right? You look at these red hydrogens. Look at the carbon next door to which they're attached. The carbon next door has 2 hydrogens attached to it. Okay, so carbon next door. So that means the peak is split into 2 plus 1, 3, and so you get, it's called a triplet. Okay, so this one is a triplet because those hydrogens are attached to a carbon, and the next door neighbour's got 2 hydrogens on it, so they're split into 2 plus 1, 3. You get a triplet. So you should be able to see now why these green hydrogens, why they're split into a quartet. Okay, because the carbon next door to them has got 3 hydrogens attached to it. Got 3 hydrogens attached. So the peak is split into 3 plus 1, 4. Which is called a quartet. And finally, if we look at the yellow one, it's an OH hydrogen, so then they aren't split. So that's called a singlet. OH hydrogens are not split. I suppose one way of looking at it is look at the carbon next door. Well, it isn't a carbon next door. It's the carbon to which is attached is it's an oxygen. Anyway, they aren't split. They're always a singlet. So this splitting, as you can probably imagine, gives if you look at a spectrum and you don't know what the compound is, the splitting of each peak can tell you an awful lot about what the structure of the compound is. So just to summarize then, with 1H NMR spectra, you get a series of peaks which correspond to different hydrogen environments. And there's 3 properties of each peak. There's, first of all, it's the integrated value. That tells you how many hydrogens in that environment. So a CH3 is going to have an integrated value of 3. CH2 will have an integrated value of 2, and so on. Then there's the chemical shift. Okay, how far it is on this x-axis. That tells you how close it is to electronegative elements. So it gives you an idea of the environment. And then finally, the splitting. That will tell you how many hydrogens are on the carbons next door, and that provides a lot of information. Okay, in the next few lessons then we're going to look at some example spectrum of different compounds just to give you a feel for how NMR works.